We now move on to have a look at the use of pointers within C++. And we're going to start off really by introducing them, saying a little bit about what pointers are and also why they're important. The reality is that pointers are actually fundamental to the execution of programs on really any computing device. They give us a way to refer to different locations within memory. So basically a pointer just simply is a memory address, or points to a particular address within memory. In some languages, obviously C++, you can access, manipulate pointers directly. In other languages, and indeed most high-level languages, it tends to be something that happens under the scene. That, for example, within Java and C#, the closest you get is the notion of a reference. Whenever you are using a reference to a variable, effectively under the scene, that is a pointer. But you never access that pointer directly. You're always referring to and accessing the thing that it points to. But we'll see when we have a look at this within C++ that it is a slightly lower level of control that's afforded to us. By way of a rather obvious reminder, but I put it in here just to introduce the notion of what a pointer is. It ties into the idea of a variable. So variable, we've got a few things here. We're going to have a location within memory that variable is stored. The type of the variable will tell us how many bytes of memory we need to set aside to store it. And then if we actually were to query the contents of those memory locations and interpret that according to the type, that would give us the stored value that we have within that particular variable. So if you had, for example, int a is equal to 4, then a will refer to a particular location within memory. Because it's an int, generally 4 bytes will be set aside, and if we were to query the content of that memory, we would find the integer encoding of the integer value of 4. So, straightforward enough. For pointers, how does pointers tie into this? Well, in C++, you have what's known as the address operator, and it's the ampersand character. And what it does is that it permits us to go to any of our variables that we've defined, and if we put the ampersand in front of the variable, we can ask whereabouts in memory is that particular variable stored. So if a was the name of our variable and we did ampersand a, what we are retrieving is the precise memory address that a starts its storage at. A pointer then is simply something that points to or an address in memory. And you can have a distinction here between a pointer variable and a pointer value. So if I define a pointer variable, same as our normal variable, except that a pointer variable, what it holds is a pointer value, and that pointer value is a particular location within memory. So by changing the actual value of our pointer variable, we change the thing or the address in memory that we point to. We can see a few examples of here of the setup for this. So let's have a look at the fragment of code. Assume in line 1 I've got something of type T. It could be a primitive, it could be an object-based, class-based type, called a var name. So this is an actual variable. So we have declared an instance of type T. It'll have location and size within memory. In line 2, we have again our type, and then we have the asterisk ptr name. So effectively we are defining here a pointer variable, and it is a pointer variable that can point to something of type T. And in line 3, what we do is that we are assigning the address in memory that var name is stored, and actually storing that address within our pointer variable. So after lines 1, 2, and 3 have been executed, we have declared a var name of type T. We've declared a pointer name. or pointer name, and we have set the contents of pointer name equal to the address within memory that var name is stored. Now, for a pointer, obviously it just points to a address in memory. It's important that a pointer variable it's not just a memory address, it has to also know, well, what am I pointing to? The reason it needs to know that is that by getting the type, it knows how to interpret the information stored at that particular address. So if we say we're a pointer to an integer, then it might interpret that address and the next 3 bytes after that address as an integer value. If we said we pointed to a double, then we would maybe interpret the full 8 bytes around that location as a floating point variable. So you need to have these two things tied together. Here's an example of how things could be set out within memory. So over on the left-hand side, we've got a couple lines of code. We have line 1, int data, and it's an integer value, and we're setting it equal to hexadecimal value 56. We're storing within our data integer. And on line 2, we're declaring an integer pointer, ptr data, and we're setting that equal to the address in memory the data is stored. Now let's have a look at how that is set out, and you see that over on the right hand side. Little aside before we get on to this, integers we said are generally 4 bytes in size, doubles generally 8 bytes in size. How big is an actual pointer variable? It depends upon if you're running in, say, in a 32-bit or 64-bit environment, and even then you can have smaller or shorter pointers than the full 32 bits. But in a 32-bit environment, pointers don't need to be any more than 4 bytes in size. In a 64-bit environment, they don't need to be any more than 8 bytes in size. That's generally how big that they are. So here in this example, we're assuming we're running on a 32-bit environment. Sake of argument, so let's say we go to line 1, we're processing this, we say, okay, we need to set aside a chunk of memory to hold data, storage of data, that integer. And let's say hexadecimal address 1000 is where we allocate for the storage of data. And there we're reserving address 1000 out to 1003. And the value within that, so we're storing the integer value of hexadecimal 56. And you can see this then in the first 4 values, that effectively at address 1000, if we're to interpret those first 4 bytes, we would interpret them as an integer value containing hexadecimal 56. Line 2 then is where we allocate our pointer variable. So assuming this is a 32-bit environment, we will allocate then 4 bytes to hold that pointer variable. And because we've declined line 2 after line 1, we just declare next location in memory. So location 1004 hexadecimal, we reserve an additional 4 bytes for the storage of pointer data. And what we are initializing it to is the address of data within memory. So if you have a look at the contents that we're storing within pointer to data, you'll see effectively there it is hexadecimal address 1000. That gives you a bit of a feel for how we have set these different things out in memory. Now, if you have declared pointer variables, and we've seen how we can do that, and we can see how we can store a particular address within a pointer variable. One of the things you probably will want to do is to access the contents of the thing that you point to. So there's almost 2 steps to this. So I point to something, I have to go to the thing that I point to, and then I want to access the content of the thing that I have pointed to. So it's known as dereferencing of a pointer or an indirection operator. And in C++, we're using the asterisk symbol as a way to signify that we are not simply interested in the location in memory of the pointer, but we're interested in the value in that location in memory. So if ptrnum is a pointer to an integer, then asterisk ptrnum means the value of the thing that we're pointing to. You can see an example down here. So over on the left hand side we've got a remarkably simple function, add or int, where we're adding in two integers, num1, num2, and we're simply returning that out. So our add function takes two integers, gives you back their sum, nothing more than that. And in line 5 we're calling this, we're not dealing with the return type, and we're passing in two integers and we're getting back their sum. Over on the right hand side you can see a implementation that uses pointers, and it does exactly the same thing as on the left hand side. You will get exactly the same answer, though the one on the right actually is a little bit more inefficient, or a little bit slower. So there we're returning an integer, same as before, still called add. In this case we are accepting in an integer pointer, so num1 points to a integer somewhere within memory. Num2 is also an integer pointer, so it points to an integer somewhere within memory. So what we accept in to this are two effectively memory addresses of integers. We then return, and here we're using our dereferencing operator, the value of the thing that num1 points to, and we're adding to that the value of the thing that num2 points to. And you can see in line 5 when we're calling it, in this case here we're calling it, we have to pass in an address. We can't pass in an integer because it takes effectively a pointer, it takes an address as the parameter. So here we're adding the address of some int and the address of some other int. Now obviously the version without the use of pointers is cleaner, but I just want to show you something that is equivalent. It does raise the question of why would we use pointers? Why? There's actually two reasons, and it comes down to the relationship between pointers and arrays, and we've yet to look at that, but there's a very powerful relationship between pointers and arrays that if we have a pointer into an array, then by changing the value of that pointer we can jump across and between different array elements. The second one, and this comes down to the heap. Within C++, we're able to allocate a chunk of memory. We can say that we want to reserve a new array or a new instance of a class, and that will be memory that is set aside somewhere within the heap. So it's dynamic memory. We don't know where exactly we're going to get within the heap. It depends on what else we have on it. So because of that dynamic allocation, what we get back is the memory address of the thing that we've created. Effectively, we get back a pointer to whatever it is we've created on the heap. So we need to use pointers simply because of dynamic allocation. So that's the two reasons we'll use them. But at the top is important that the pointers are, there's an extra layer to pointers that actually slows them down. If you think about accessing a variable, say I had my integer and I wanted to access the content of it, the integer effectively is address in memory. I would go to that address and I would interpret the values at that location. If I have a pointer variable, then I've got to first of all go to the address in memory of that pointer variable, look at the data stored in memory there, and interpret that as an address in memory. So that's the thing I'm pointing to. Then go to that address in memory and interpret the information at that value. So it's two, if you like, two steps to get to the data. So actually it's slower to access things through a pointer than simply it is to look them up directly. A little bit about pointer style. There's two common ways of doing this, of actually styling this out. So in line, the fragment of code at the top, we're calling a function called foo. It accepts an integer pointer, and the common format there is you have the type, followed by the pointer symbol, then a space, and the variable name. If we're declaring pointers, however, then we use a different style, and you can see that below, where we have our type, in this case an integer, we've got a space, then we have our pointer and the name of the variable, and both of those are attached together, and we can see there we're declaring two integer pointers, pointer int1, pointer int2. From the language perspective, it doesn't care where you put the spaces in. You can, or you cannot if you want, you can have a space that can be before or after the variable type. You can put what either before or after, you could have one before and after. It's entirely up to you. The conventions that are shown here, they've arisen because it's cleaner to do that. And you can see some examples at the bottom where we don't adhere to those, which actually makes it slightly more confusing. So if you look down at the bottom, in line 1 we have int star. So if you're scanning this, you go int star, okay, it's an integer pointer, a comma b. So you might think then that a and b are both integer pointers, but that's not how the language would interpret it. Instead, a is an integer pointer and b is just an ordinary integer. Line 2, there we are declaring two integer pointers, a and b, but it looks a little bit ugly that we have int star and then space an a and then a b star. So the two conventions that we have set out here are ones that if you follow, and most, basically all C++ programmers will, it helps you more clearly communicate what it is you are intending. There's a deeper point to this, and it's written here, the code should be written so that the meaning is apparent in the eye of the beholder. A lot of the modules that you'll do, generally there's a quantity of marks set aside for the code quality, the layout, the structure of it. And it comes down to making sure that you've written things in a way where if another programmer, or even yourself at a later point, is sort of quickly scanning through your code, that you have structured, laid out, formatted, selected variable names, things like that, in a manner that it actually aids the understanding of the code, that makes it more easy to understand. And that ties into the things that we write. Generally, there are two audiences for it. Sure, we're writing things that will get to be compiled, turned into executable code and get to be executed. But we're also generally writing things that other programmers will have a look at as well, even ourselves at a later point in time. So making sure that it is written in a way that aids this process is actually quite an important element of being a good programmer. So by way of rounding off this introduction to pointers, and in the next sort of talk on pointers, we'll have a look more about how they end up being used. Pointers are wonderfully powerful. We've only sort of introduced them in a basic form here, but they do enable us to do a lot of things. In essence, they give us a flexible means of manipulating and accessing memory. And with arrays, that's going to be it's going to be certainly of benefit. Again, you'll see more in the next talk that with raw pointers, just basically addresses within memory, we need to be careful that we access them correctly, that we're not jumping outside, for example, an array and accessing areas of memory that we shouldn't access. And the most important takeaway from this introduction is that when we're writing our code, the most important thing is to make sure that its meaning is apparent in the eye of the beholder.